Thank you for joining me today at the talk about apparently unexpectedly broken expected. Let me introduce myself first. My name is Vitaly, and I'm working at Remarkable. One of our main products is I have it with me today. This is a new one. We released it this month, I believe. So this is quite portable on move and good for everyone who is doing a lot of notes within conferences and doing some other stuff that requires writing. And furthermore, which is important for this particular talk, almost all of the code samples I want to demonstrate today that are actually running on this guy, which is super cool. So, oh, by the way, if you want to give it a try, I have one with me. So just come after the talk and see what the experience is. The agenda you can read, I don't need to repeat. I just want to mention that there was a larger version of this talk. I gave this sprint at CPP Now, so that has much more technical details inside, but pretty much the same meaning and the follows. So I'm not sure whether it's released, but if you're watching the recording, so it can be released, so you can navigate on YouTube and see the full version with a lot of technical details. So in this talk, I'm not going to touch a lot of theory. There will be super simplified code snippets because apparently all of the code is full of templates and hard to read in. So we are going to do the simplified version. And I'm going to propose some, changes, improvements to the standard implementation of the expected. Yeah, that's it. We can start. First of all, examples and experimental implementations are on GitHub. There is the first QR code. This one is the library itself with many functional primitives and stuff, and the second one is expected itself. You don't really need to probably memorize or scan it right now. I will share slides in the Slack channel just after the talk. So let's talk briefly about studio expected. And my first question to you guys, are you familiar with that? So don't lower your hands yet, so you use it in production? Great. So, but I just need to do a quick recap. It's at least 30% of audience familiar and use it. It's very cool. So what the expected stuff, it represents two values. It's either expected t, it's a correct value, or unexpected e, which usually stands for an error. The union under the hood, we will talk about it later. And it has monadic operations that allows you to change some certain actions based on the result inside the expected container. This is a very basic example of usage. I usually use this notation of the box. It's kind of a box where I can put something. And in this case, it's either an integer value or some custom error. We don't care what kind of error is it right now. And then once you put it, for example, 42 here, you can access it by using .value and print this value, for instance. But should we, for instance, use the expected this particular way here? We have some function to load widget. We are getting widget somehow and assuming that this auto here is expected. So we check in whether this has value or something else. Fn has an error. We access an error and print it. Do you see what's wrong here on this particular slide in else branch? That's correct. So we just check in if has value and if it doesn't contain a value. So we're still trying to access value. Don't even try to guess what happened in this particular case. We will talk about it. So, but how we can handle this? We have monadic operations to rescue, and with these monadic operations, it's much more complicated to do such mistakes. You can see the monadic operations. Those are not the main point of this particular talk, but still there are 4 of them, and 3 of them are on slide. So the first is and then, and this handler will be invoked only and only if there is a value inside the expected. So it's impossible to access an error here from this point. Another similar one is transform. The difference between that you can, for instance, from and then return the error and it returns expected, and transform can change the type of value and it will be wrapped into the similar expected for you. And or else handler, that would be called only on the case of an error, and you can do whatever you want with an error or even roll back from error to the value. That's how you can use it, and I hope you will be using it if you haven't expected to process. So we have those for monadic operations, the transform and transform error, that's the simplest one, where you can process the error or value and change the type of it. And then on or else, that way you can do pretty much the same, but the difference is that you can either return an error from and then or value from or else or rollback, and you can change either value or error type respectively, but not vice versa, to do not lose the information about the type of either value or an error. If you want to learn a little bit more about monadic operations, how to use them, I gave this talk last year at CPPCon, so please welcome and watch. I guess it's already released on YouTube. Let's have a quick look under the hood of the expected. So what we have here, we have 3 major types defined: unexpected, to mark the things as unexpected, and I will tell you why we need it in a few minutes. Then bad expected access. So surprisingly, we have the class for exceptions in expected. And then we have expected itself, where T stands for value and E for error or unexpected. So this is the implementation taken straight from the standard, and I believe it looks pretty much the same in the GCC implementation. So what we have here, it's a union of T value and an X, and please see that it's not wrapped in unexpected, so it's just an X. And we have the sign of presence of value or an error here. And this is the first issue here. The value type and error type can be the same. So, and if you didn't know, here union allows you to have the same type, nothing wrong here. So that's why this code is perfectly fine code. You have an expected of string and another string. And that's the reason why you might need to have stood expected to distinguish what you return. That you either return value or an error out of it. But the question is, do you really need it? And like, from my practical experience, if this is the case, it's either you experimenting with something or doing something probably wrong with your architecture, because the error type is usually a strong type that defined for your library or on component level. The consequences of the existing implementation, we having an extra abstraction for unexpected. The API users, they must explicitly specify this type. The implementation is like quite complex with many different restrictions, which is probably not something wrong for users of the API, but it makes it a little bit complex to implement. And it's harder to use stood variant of T and E under the hood, which can give you many benefits. I'll tell you like in a moment. So, but what's wrong with that, with stood unexpected T? It's additional abstraction. It's bad. You don't have to use too many abstractions if you don't have to. And it's not quite symmetrical. There are 2 examples from other languages. On the side, left-hand side for me, this is, I believe, from the language should not be named in this conference, but this one from Rust. So, and you can see this absolutely amazing symmetrical stuff with OK and error here. So, OK, you want to have a result, you either wrap it in an OK or error. Looks cool. And on this one, it's a little bit more functional stuff, but it's from Scala. It's either. It's slightly higher level or more generic abstraction. But the thing is pretty much the same. So left and right, you wrapped, it's quite symmetrical, but not in C++. So we have the expected itself as expected and unexpected to distinguish what the unexpected value. But what if, just think, if we had some simple restrictions to stud expected, we say restrict that the value and error cannot be the same and they cannot be mutually convertible. In this case, we can easily declare new expected and use stud variant either by inheritance or somehow else. So we have base t is variant and use all variant constructors. And we can use monostate when the value type is void. And error obviously cannot be void. If you want to have void error, you should use stud optional, probably. So, but what can we get from this? We reuse existing abstraction. We can super simple implementation of that small amount of lines of the code. And most of the implementation will be the test code to check the entire invariant. And we can use std_get and all variant-related utils. We don't even need to have the regular interface. We can only monadic interface. And for the cases, there are cases where you need regular non-monadic interface. Talk about it later. And the first important stuff, you can use std_visit. And std_visit is like nearly pattern matching in V, especially if you have some abstraction like the match that can give you a little bit better abstractions than overrides for pattern matching. That's cool stuff. The section conclusion here, for what we propose, if we impose those restrictions, we can get simpler implementation, drop redundant abstraction, use standard utilities from stud variant, we just reuse the entire abstraction. We can use nearly the proper pattern matching, which is cool. But the cons of which we have type restrictions and we can have potentially negative impact on performance by using stud variant, which perhaps shouldn't be the case for two alternatives. And with reflection, if we say implement variant different way, that can be better. Cool, but I briefly touched it, and we have the second issue. We have two interfaces. We have monadic interface and the regular interface, and they are easily accessible of the same level of accessibility. So as a user, imagine you use your ID, you just put dot or something, and then everything is available for you. And then available value is available. And what you're going to use is like what you can find in the internet or what AI tell you, right? So this API duplication we have, and on this side we have monadic version, and this side we have just regular if-else version. And they look super close. And at a glance, the regular interface, I would call it procedural code. So that looks simpler, less verbose, right? But we already discussed a little bit why you should use monadics. That's only one pros of them. Benefits we have, I just put it one more time. It's safety, it's easy to propagate either value or an error, and it can be used in most of the cases. Pretty much 95% of use cases will be probably covered by monadic operations. However, okay, that's another example I have. You can use even monadic operations in unit tests if you want. You can use it this way. That's a very funny example. The cache framework used here, so you can calculate area of a shape. We all love shapes, many mentions of them. So then we do calculations. Then on the right side, we just check if it's actual expected check. And if an error, we just fail and we format in the error onto string and show it as a failure error. You can even do it this way because the reason why I put test example here, because many people ask, hey, how do I test my code with monadic? So that's how you can do that. And there will be an alternative approach. I will show it at the very end of this talk. However, there are still places where you need to have a regular interface where you should use non-monadic operations. So that's a main function, obviously, or analog of main functions. That's you bubbling up the expression. You need to have some handler, and then you need to extract the thing. In a sense, you can use it with monadic in some cases, but you most likely in main, you need to access it by value. There are libraries boundaries, so where you might need to remap to do some actions where you have some glue code, right? So, and there is another thing they call I called it integration boundary, and I will show you an example. The example of integration boundary is like can be UI interface. Are you familiar with Qt QML? So great. The Qt QML is like things to write UI in CPP, or mostly in QML, which is a different language. So imagine I want to expose something, like I have a window layout thing to manipulate windows. I can add a window by URI on my layout and do something else after. Here I have my class, window layout that inherits from QObject to be integrated with Qt type system, meta type system. Here I have an invocable method that can be invoked from QML context, and my class that it just has a shared pointer to the actual implementation. And in this particular case, in the add function, so I mean, I cannot propagate, for instance, an error as expected object to the QML to another language, because it first doesn't have the abstractions for this proper abstraction. If you try to write the abstraction, it won't be that easy, because you don't have full control over the lifetime of what you return. You just hand it over to this v4 runtime. The half of JavaScript used the in QML. So, and then what you do is a common way, and what is expected by many QML engineers or UI developers. So you just print an error, print what's wrong, and that's pretty much it. So that's how it works, and it's what's called integration boundary, potentially. We have some conclusions here. So like Monadic API is safer than regular API. That should be default option, and probably the regular interface should be not that easy accessible. If we, for instance, had the thing from the first part, from the first issue, if it was a variant where you can use std_get to access values, it's not just a part of the regular interface. So by default, you as a user are getting just and then or less or something like that, which is kind of good. Yeah, and you can just reduce the risk of using wrong API and introduce more monadics to the code, which means safer code. So the third issue is that there are no customization point. And by this, specifically, I mean no customization point for error handling. The standard library is like, well, doing good in many sense for introducing customization point, but not for expected, unfortunately. So, and we have a problem, like the huge one. So we want to access a value through the standard API. So if there is no value, if there is an error in the first case, the exception will be thrown, but expected access. So if you use another operator, star or error or something, then it's UB. And if you use an error, for instance, similar in this value, it's also UB, which is probably not great. And I mean, like, there are the number of issues with this API. So it's not symmetrical again, it throws. And why it's bad? Because you usually expect it as an alternative mechanism or as a main mechanism for propagation error, for bubbling up errors. And then it can throw. And introduce UB. I mean, we most likely love UB in CPP, but it's not always nice. And you cannot customize. Just imagine I want to customize, I want to do whatever I want. When an error occurred, I want to print stack trace, send it to my login system, do something else. I cannot do that. Here I talked, by the way, about different error handling techniques. Here at NDC TechTown, if you want to learn more about different ways or different approaches, how we can handle different errors in different manner, just please watch this talk. Is definitely available on YouTube. So, but to the customization point. So if we want to customize it, we can have it. It's just one of the implementation. So if we want to access a value, we just check in, okay, fine, if there is an error and there is a custom value handler found for this particular type, we just invoke it like this. Or if it's not found, there is a default handler, and default handler can, for instance, send sentence to terminate or something like this. it's in case if we still need regular API non-monadics. So, and if everything is fine, we just use std_get. I'm assuming that my implementation uses std_variant under the hood, so I just can get value type like this, and it works. So, and what can be default handler, for instance, it can look like this. So if something goes wrong in the const evaluation context, that's the technique that will print it on compile time, and otherwise we simply terminate. So that's very cool if we have this customization point, but still. And if we want to implement our own custom handler, we can do it like this. So it's just in our namespace. So, and then we do it, and we can end up with terminate, but we can handle, we can log, we can print stack trace, and so on. Just implement it for our type, and we're good. However, this is not that easy. It's not as easy as a pie, because like technically handlers can throw as well. Should we impose more restrictions? Shouldn't we impose more restrictions? Should we terminate by default? Should we do something else? What should it be like singletons, like getter, setter, or template specialization, or else? Or function signatures are also quite unclear. What should goes onto this termination handler, like the entire object, error only, something else? So with termination handlers, there are more questions than answers right now, at least in my point of view. But can contracts in CPP 26 help us? Potentially. Potentially, yes, they can help. So, but as of now, they defined in CP26 only for this operator star arrow, but not for value. It's inconsistency again. So there are customization points, certain customization points. However, the implementation details for contracts are still questionable. It's unclear. There are now experimental implementations, at least 2 compilers, probably already 3 major compilers. I don't really remember about MSVC. Probably it's here. And then we can still have potential UBs and how those contracts will behave across the library boundaries, and in some other situations it's quite unclear, and when can we be able to potentially use them. But it would be quite good to address all of this or cover all of these APIs with contracts. It would be super cool. As the conclusions, we have no customization points that can be quite useful. And there are many questions to API design of those things. And contracts potentially could help. But if we had std variant plus Monadic API either attached to the class itself or free through pipe, that we would never had those issues. We have another thing. So, are you familiar with all these things? Bind back and bind front. Stud bind back, bind front. Not many people. I do have the very short recap, one slide about it. So just imagine we have a function for adding things. So like add 2 ints, and we want to transform it into another function. Here on the second line, we invoke this stud bind back, and it means that it binds 1 to the second as a second argument and returns you new function, add 1. So now can be invoked of single argument, and the second will always be 1. So and this one prints 3. So that's how bind back works. And the same thing, but from the opposite side, is for bind front. So imagine that we have increment function that has it by reference and this by value. So it just adds second one to the first one. And we have a here. So and we always want to increment this particular a. We invoke bind front, and as the first part, we just bound the reference to this a. We're using stdref here, which returns std reference proper, and this will be bound. And then we want to increment an a. We'll be incrementing only a and increment a by 2. And this, I mean, I don't have it here, but the a will be, what would be the value of a, by the way? Interactive element. That's correct, because we have this a initialized with 0 by default. Cool. So, but I mean, are there use cases for these things with monadic operations? Lambda functions, you can say, yeah, sure. I mean, usually that would be lambda functions, but lambda functions can potentially reduce readability of your code as well, especially if they're misused. And also because of the too noisy syntax of lambda functions in C++. They're super powerful, they can do a lot, but the syntax itself can be super noisy. So lambda functions can be too long. Some people prefer writing lambda functions on 50 lines of code. There can be too many lambda functions, and they can be nested. So like if you have, I'm not sure, like 3 arguments or parameters to unwrap, then there will be a ladder of 3, 4, 5, 6 lambdas. Not good, right? So there can be already functions to use, like free functions that can use in many times, and for instance have to accept one more argument, and you want to reuse it in your monadic operations. That's where bind back and front can help you. And the function you want to invoke can be a class method. So in this case, probably only one, or not only one, but the most frequent use case for bind front, it's where you bind in the object this to its method and then invoke it. So you might want to reuse it as well. And like issues here are that bind front is available from CPP20. Probably many of us use it. Are you using CPP20 on production? See, not many people using it, right? So like 15% of the audience, perhaps. So and bind back is available from CP23. Oh, of course, we all use third-party libraries and implementations where those are available. Most of us probably use. I'm not going to ask this question. But the second bullet here is that both bind back and front need to preserve the arguments you pass into it. So the next slide, I guess, or slide after, I will show what the problem here. And there is a restriction that arguments by be move constructible. So they moved on the capture list usually. So and the implementation can use extra intermediate structures like tuples, which also hits both readability and performance in a sense. This is the implementation of bind front. You don't need to read all of this, but the thing you should see here is like that there are so many requirements, like how it can be constructible, how it can be move constructible, convertible, and whatnot. So, and the main point here is that the bound args, they just forward it like this in the capture list, and they are stored. So if you use it within monadic operations, you kind of copy your arguments or move your arguments. So there is one extra step, which is you probably don't really need. So and if we make it built-in for monadics, we just have and then implement it this way. Now you can read it, and it's super easy. So you have a function in the interface, and then the optional pack of arguments you bind in back. If it has value, you invoke it the usual way. You invoke function, you pass self into the value into the function, and then you pass the rest of arguments. And this is a simplified implementation. There are many checks and everything is invocable, all values matched and whatnot. But still, so, and this approach has many pros in comparison to using just bind front as a free function. So we don't really need having extra functions, and we don't need store arguments and intermediate storage and everything. The requirements to arguments relaxed, right? If you pass in reference and everything, they will be just forwarded to the function, which is very cool. And you invoke function immediately anyways. You don't need to use to references, to C references, any other extra wrappers. And monadic operations can keep the same signature, except for bind front, but there are different approaches and techniques. So before the conclusion, for instance, if instead of marking, say, the function with bind front with a tag, separate tag, you can use like an extra tag, like just bind, and put bind as a placeholder in a place where you want to bind the main argument that passed, and then spread arguments around it. That would be pretty much working as a just bind, but without creating intermediate functions and structures. We have our own implementation of expected in our library. The reason of it was mostly the context per context. So it doesn't, standard implementation doesn't support it nicely. So, and we have at least those things are implemented like built-in bind back, and we have, as of now, even built-in like custom bind to the custom place, which is cool. So, and then the conclusion is relatively easy to have built-in bind back and front. The implementation itself is like super teeny tiny, but it's super cool in terms of practical usage. But it's not fully grammatically correct in terms of functional programming. If you like for this pure approach and pure stuff, that is probably not that cool. However, very practical. And there is an issue, right? The big issue. There are not enough monadic operations, like built-in monadic operations. I know that there are many things can be implemented as free functions, but still. And by this, I mean specifically, but before I tell you what I mean specifically, if you want to refresh your knowledge on monadic operations, just watch this talk by David Senke from CPP-Cone, and there he gives like very good overview of all of these scary things, monads, monoids, functors, and everything. But what I want to talk about this guy. This is like not about bending. I want to talk about applicative. So, and this was a talk about the applicative functor or pattern. Call it the way you want. This is a big one. And if you want to learn things into details, please watch this particular talk. But I want to make it a little bit more practical without Haskell and some other things. And if we look at the, say, canonical pattern for using this, imagine you have expected, like regular expected of some value and some error. And in a canonical notation, you have a function, you have a value, you want to apply this function to the value, or simply invoke the function of value. So in canonical form, you have two parameters here. First is the expected of function, and second is expected of value. So if there is both a valid function and value, you just invoke it. And if something is wrong, you return the error of either the function is wrong or expected is wrong or value is wrong. And here we have additional abstraction pure that just wraps our object into this particular expected that we defined here. This is quite canonical pattern. So say we want to use it. We have a function that's called toString. We want to convert something to string. That's very simple. It's toString of integer. And then we can, some functions that gets us a number, and it can fail at some point, so it's expected of int. And why there is only one int? Because we use our own expected from the previous slide, right? And error is already defined as some error, say from our library, whatever. So, and if we want to use our apply, so we use pure of toString, we wrap our toString functions into this expected thing, and then we invoke it on the number. And the result would be expected of toString, is where we potentially unwrap our function and number and invoke it. And then we do something with the result. However, and most likely in your code in practical situation, the function itself, function you want to call it, is not wrapped into anything. It's just a function, free function, lambda, whatever. It's not expected, it's not optional. And the parameter types, or the types the argument you invoke this function of, they can be not expected, not optional. At the same time, some of the arguments can come from different places and can be wrapped into something, right? So it can be kind of impure in this sense. Mix of arguments, a mix of function you want to invoke. And why I'm talking about this case? Because it's a quite real case. For more real example, we take the previous one, we have just function toString that invokes toString, that we have the number that returns expected, we want to apply. And here toString, as what I said, just a function. And integer is an expected object, but we still want to apply, we still want to unwrap, we still want to invoke, and still want to be consistent on the result. We can actually have an up-like method super close to end-zone, and those can be combined potentially. Function can be just a function call, and arguments can be mixed. So either wrapped and expected, but obviously the same expected, right? So, and they could be the regular values as well. We can have this method interface, super simple, super close. So I named it this way, that you probably shouldn't do, or we shouldn't do in the real implementation. Still, we have pretty much the same function and args, and this is a trace to say that everything can be unwrapped, invocable, so on and so forth. And we can unwrap or forward, and we unwrap it if we need to unwrap argument, or otherwise we simply forward it, and then the implementation would be like and then pretty much. How we can handle errors in this case, because some arguments can have the value, or some arguments can have an error. So we can return first, or we can combine everything. So if we have something to combine with the operation that can combine two entities for you. And the use cases for it is that imagine that we have a function, like opening a window potentially from our window navigator from previous example. We have the window navigator that used to open it, we have URI, and we have some initial state. So if we doing this code, we just, okay, fine, we get URI from some place, like from raw input, for instance. So from string, and it means that our URI can fail, right? It cannot be decoded properly at some point, so it's wrapped into expected. Then we have state, and potentially state can never fail, so it's always in regular, it's not wrapped. And then how do we use it? We get a navigator, and then we open up on open window function, and then expected URI and initial state, and there is a mix of arguments. Or alternatively, if you have it as a free function, you can get navigator, then open, expected, and initial state. So, and this is super common use case when your different arguments coming from different places, some of them are expected, some of them not expected, and you not necessarily want to invoke pure on every argument. That's why the up method is super useful in real applications. What we can do for the future improvements with up stuff, that's just potentially it can be a part of and then with a certain tag. I know, again, it's not super pure approach, but still would be super practical. And then we also can combine errors if supported, or just return first or not, or something. We just might provide a different customization point on how we want to handle different errors. And this is a small conclusion of these sections. We have potentially can have built-in applicative, and this is super valuable when we have many different arguments that come from different points of our program, and they are inconsistent, happen all the time. So it might be not general functionality, that's why I'm talking about the free function. And it's not necessarily belong to the main expected interface, unless we have more fluent interface that can be changed through pipe or bind or similar. But, I mean, all of these things are required to modify the existing abstraction, right? And it probably will never happen, take into account how the standardization work. Or, I mean, happen, but in 15 years or something like that, and will never be deprecated. So we can actually do a lot of changes, if not all changes I said, with simply freestanding function or the piping operator, or we can choose another one. And don't really use standard interface. Technically, it's nearly stood variant of value and error with some fluent interface. I would call it this way. And if we take my first example, and then simply change all dots to pipes, we can get pretty much this. And what it looks like ranges library, right? Pretty much. So we already have this syntax introduced, and we can reuse it. So, and another thing that I promise that can be used with this interface, with the free functions, we can create unwrap-like functionality for tests specifically. So we can use expected, and this abstraction can fail if an object contains an error, and it can return value if there is a value. We can have simplified implementation like this. So just pipe operator with this structure with unwrap t with very famous name. So then if there is an error, we invoke fail. It's again specific for the test framework I used for examples as catch2. So it fails immediately. And if there is a value, we return a value. And then we have unwrap like this. To the usage example, we have simply test case. We, for instance, get in some shape. We calculate area of this shape. And then we can do pipe unwrap. And in this case, we can have linear code. So that fails normally if there is something wrong. And that doesn't fail or just return you a value if nothing is wrong. That's the alternative approach how you can test your code even without monadic operations, but still staying quite safe. And as a conclusion of this section, like almost, I guess, all existing monadic operations can be implemented with the pipe operator. Many extra monadic operations can be implemented the same way, and you don't really need to touch the interface. You don't need to recreate exception from scratch, so expected, and which is very good. Unless, of course, you have very specific use cases when you have to do that. And I have some final thoughts on all of these things. So as a conclusions, like current interface of stud expected has definitely some certain issues. It's probably not fully broken, but rather inconsistent. And some of those things result to quite error code. It's super easy to write the incorrect code, especially if you have never used these abstractions before. So you just start using it, and as I gave you an example with this .error.value, that's super easy to introduce this code, and especially if it's not covered by tests properly, because apparently not many people cover negative scenarios, it can hit you like somewhere close to production. The interfaces, like some of the practical useful functionality, might not be that pure, but we need more practicality, I believe. And most likely, you might need to create your own expected, and especially you might need it if you want to use it in context per context. So because apparently even if you create your own expected context, some of the operations might not be supported, say, by stud variant in some of the tool chains you have. So you might need to use union under the hood or whatever. And the creating pipe-like interface for standard expected can be a good alternative for it, which is absolutely nice. And with that, I strongly believe that my last slide. Thank you, guys. Please turn it back. Thank you. So if you have any questions, please ask now. I don't think we have a mic for the audience, but I will repeat it for you. And if not, we can talk after. I don't want to hold you for the lunch. Shoot.
Specific examples of the monadic operations you are missing?
The question was about specific examples of missing monadic operations. That's I do for applicative. That's one I showed. But for others, I also have, and we can talk about it. Another questions? Yes, please.
Have you looked at other open source implementation of the suspected .nano or something like that to see if they have the same?
Yes, but that's probably a little bit more relaxed in comparison to the standard library in terms of things, and it's not actively supported yet. If I'm not mistaken. So, it's like maintained or something. So you do not maintain it, I guess, anymore.
I don't do a lot of work on it. Yeah, it's true.
Oh, okay. So yes, the answer to your question, direct answer, yes, we considered some alternatives, and we ended up creating our own expected because of the constexpr context. So we need to use it in constexpr with some things and with some additional operations. So that was the reason. Yeah, other questions? Yeah, great. Thank you, guys. See you around.